Welcome to the next section of Chapter 7. Here we're looking at transformations once again. This time it's going to be looking at exponential and logarithmic functions. As we've seen several times in the past, transformations are all going to be the same. The only thing that's going to change is the example. This time we're going to use exponential and logarithmic functions for examples instead of polynomials or quadratics or lines or absolute values. We have a couple more transformation lessons throughout this year, but it should be getting pretty good. One of the big focuses of Algebra 2 is functions and being able to get any function by using transformations of a parent function. Being that this is a lot of stuff that we've already seen, we're going to go through that. It's going to go pretty quick. But there's some cool stuff that happens with exponential and logarithmic functions that we'll get to see as we're doing this. So, without further ado, let's look at some learning targets. The first one, I can transform exponential and logarithmic functions by changing parameters. Yes, you can make the transformations. Second one, you can recognize the transformations. Given a function, how is this transformed from the parent function? They're the same types of questions that we've seen throughout the year with this type of topic. So, let's see. Let me get a laser pointer here. Aha. All right, so the first one we're looking at is translations. The two functions that I've picked for this one, we have f of x equals 2 to the x, and f of x equals log x. Notice the exponential one is green, the log is purple. Also, the exponential one has an exponent, and the log one has a log. If you're having trouble seeing those colors, you can always tell by just what the equations look like. And so, this works, like this could have been e to the x, could have been natural log, we could have had log base 5. The real reason why this is just log base 10 is because it's obnoxious writing different bases for every single thing. Nothing that we're going to do is going to change a base, except at the end we'll see what happens with the change of base formula. So, translations. We have rules, we have horizontal, we have vertical, just like everything else. Horizontal, g of x equals f of x minus h. We're moving at h units to the right. Remember, anything we do horizontal is backwards. We're going to the right, but it's minus. And so that makes that number always backwards. Oh, our nice horizontal line. Remember the horizontal line. All this stuff up here is the same every single time. In fact, I copied the slides. I did. I didn't even retype it. I copied it. It's the same horizontal line. Yes. The colors are the same. I did change the examples, obviously. So let's shift 3 units to the right. So our general equation, g of x equals f of x minus 3. This does not matter what kind of function we're looking at. But what it says is that we're going to take the x and we're going to change it to x minus 3. So for our exponential, we take the x and it becomes x minus 3. Notice everything horizontal is going to happen in the exponent. Everything that's not horizontal will happen outside of the exponent. For the log, we take the x, we change it to x minus 3. Everything horizontal is going to happen inside the log. Everything vertical is going to happen outside the log. So, vertical, we're going to add k, and we're going to do it to the function itself. It happens outside, and that'll move it k units up. So if we wanted to move it 5 units down, which would be negative 5 units up, we're going to have g of x equals f of x minus 5. So we're going to take our f of x, and we're just going to subtract 5. Here our f of x is 2 to the x minus 5. The log of x, minus 5. With logs, though, we don't usually put the minus 5 here, because is this log of x minus 5 or log of x minus 5? Like, is it supposed to look like this? And so to save the confusion, we put the minus 5 in front. Make it negative 5 plus log x. It means the same thing, but it's to differentiate between these guys. So it just makes things a little bit easier. Now, translations, we can do both horizontal and vertical at the same time. So let's move it 1 unit left and 2 units up. So moving it 1 unit left, we're going to have f of x plus 1, and 2 units up, we'll have a plus 2 at the end. So that means we're going to change the x to x plus 1, and we're going to stick a plus 2 on the end. So let's look at our exponential function. F of x equals 2 to the x. Let's change the x to x plus 1 and stick a plus 2 on the end. There we go. That would be our translated exponential function. For our logarithmic function, we're going to change the x to x plus 1 and stick a plus 2 on the end. Here we have parentheses, so it's not as important that this plus 2 is in front, but it still easily could be. If we remember about our exponential functions, they have a horizontal asymptote at 0. A horizontal asymptote. Remember, it doesn't get below 0. 2 to the something is always going to be positive. The only thing that's going to change that horizontal asymptote is a vertical translation. This one, we went down 5. The horizontal asymptote is now y equals negative 5 instead of y equals 0. It just moved down 5 with the function. Logarithmic functions have a vertical asymptote at x equals 0. The only thing that's going to change that is a horizontal translation. We moved it 3 units to the right. The asymptote is now x equals 3 because we went 3 to the right. So the asymptote moved 3 to the right with us. And so that's the only thing that's going to change. Stretches and compressions won't change the asymptote. So that's the only time you have to worry about that. Speaking of stretches and compressions, let's look at those. So we have horizontal and vertical. We have our nice line. Horizontal, g of x equals f of 1 over bx. Remember, with these guys, we're multiplying, and with horizontal, everything's going to be backwards. So instead of multiplying, we're actually dividing. And remember how to tell if it's a stretch or compression. Stuff's not changing. If b is less than 1 but bigger than 0, it's compression. If it's bigger than 1, it's a stretch. So let's do a stretch by 2. So we're going to have 1 over 2x, which means we're going to replace the x with 1 over 2x. So we have 2 to the 1/2 x. Notice this 1/2 x is an exponent. And we can do something with this. It's not quite as easy to see here. We'll look at that a little bit later in a different example. But this is where things can change a little bit, and it makes it kind of fun with exponential equations. For log, the x changes to 1/2 x, just like it did for the exponential. But now this one we can kind of see. So we have log of 1/2 x. That's 1/2 times x. When we're multiplying stuff inside of a log, what does our property say that we can do? It says that we can add 2 logs. It's log of 1/2 plus log of x. Log of 1/2 is just a number. We have a number plus x. What kind of a transformation is a number plus our function? If you're thinking, oh my gosh, that was a vertical translation, that's what we just did on the last slide, good job, you're paying attention. Yes, a horizontal stretch or compression in a log is the same as a vertical translation. I mean, that's crazy. It's awesome. And it's fun. So that's a stretch. Let's look at a compression. This is where we're going to be able to see what this exponential one does too. So compression by 1/3. 1 over 1/3 is just 3. So we're going to replace all the x's with 3x. So for our exponential equation, we have 2 to the 3x. 2 to the 3x, we have our exponents are being multiplied. Well, how do we multiply exponents? When we have a power of a power. This is 2 to the third to the x. 2 to the third is just a number. It's 8. It's 8 to the x. So a horizontal stretch or compression will change the base of an exponential function, which is just kind of fun. This one does it too, but 2 to the 1/2 is a little bit tough for us to think about right now. We'll get to see what fractional exponents are like in chapter 8, and we'll have fun with those there. But down here we can see it with the 2 cubed. It's 8. Let's do the same thing with the log. We're going to replace the x with 3x. And just like up here, we could split that up. Log 3 plus log x. This is, again, a vertical translation, which is the same as a horizontal stretch or compression with logs. I don't know. I get goosebumps thinking about that stuff. It's just crazy. Yeah, it's okay to laugh. All right, so vertical. We just multiply to the outside of the function. So, and stretch and compression is the same rule. Let's do a vertical stretch by 4. We're going to multiply 4 times the function. So that'll be 4 times 2 to the x. Can we combine 4 times 2 to get 8 to the x? No. Remember, exponent before multiplication. Order of operations is still there. We will come back to this in just a minute, though, to see something cool here. But first, let's look at the log. Log, we have 4 times log x. Let's see, we have something multiplied in front of the log. Where could that go? Oh, that's right, the power property. Power property says we can take this 4 and we can stick it up into the exponent. So if we have log of x to the 4th, that's a vertical stretch by 4. Is it possible you'll see something like this? Maybe, partially just because it's cool. But remember that 4 could go either place, and it means the same thing. Let's do a vertical compression by 1/5. So we're just going to multiply 1/5 in front of each of them. 1/5 times 2 to the x. That's about it for that one. And 1/5 times log x, which again, that could be written as an exponent. And so I said I'd come back to this one. And the same will be true down here, but this one's going to be a little bit harder to see. But this one, we have g of x equals 4 times 2 to the x. Well, 4, couldn't we rewrite 4? Isn't 4 2 squared? And so we get 2 squared times 2 to the x. So we're multiplying two things with the common base. What do we do if we multiply two things with a common base? Like, what would we do if we had x squared times x cubed? We'd have x to the 5th. You add the exponents. So here, we could add the exponents to get 2 to the x plus 2. Well, what kind of a transformation is that, where we're adding a number to the x up here in the exponent? Yeah, that would be a horizontal translation, again, from the last slide. So a vertical stretch of an exponential function is the same as a horizontal translation of an exponential function. Now notice we had to multiply by 4 to get a horizontal stretch of 2, so it doesn't go evenly, but it still does the same thing. It's awesome. So vertical stretch, horizontal translation, that's exponential functions. Horizontal stretch and vertical translations are log functions. It's crazy. All right, well, let's move to the next slide. I know you guys are probably getting excited about this. So, reflections. We have our functions. Reflections are the easy ones. We have our horizontal and vertical. The toughest part about reflections is doing the right one, because we have to place the negative either in the x or outside. But it won't say do a horizontal reflection. It'll say reflect across the y-axis. Y-axis, usually people think y, they think, oh, vertical. Nope, across the y-axis is horizontal, and across the x-axis is vertical. So if we do this, like these are the rules. G of x equals f of negative x, g of x equals negative f of x. So if we take the x and we make it a negative x, we get 2 to the negative x. We could change this around a little bit. That's 2 to the negative 1 times x. 2 to the negative 1 is just 1/2 x. So a horizontal reflection will flip the base to be a reciprocal. Kind of fun. And for logs, we have log of negative x. Nothing really happens here. I mean, that could be negative 1 plus x, but it's still, nothing really goes there. We just put the negative number in for x, it becomes positive. The domain of a log function is x is greater than 0. So when we flip it, now x has to be negative so that this could be a positive number. So it changes the domain to be x is less than 0. For vertical, we just go negative 2 to the x. Nothing really happens except, again, it switches the range. 2 to the x is always going to be a positive number. So our range for an exponential is y is greater than 0. Well, then we slap it with a negative, and now it's y is less than 0, because all the numbers will be negative. And for logs, negative log x, well, this negative is a negative 1. It could go up in the exponent, and something to the negative 1 is just its reciprocal. So a vertical reflection in a log could just be a reciprocal of the log itself, just like the horizontal reflection in the exponential is just a reciprocal of that base. And speaking of base, you're probably wondering, what about the change of base equation that you teased us with in the beginning? I want to know. Oh, good. I'm glad you asked that question. So, change of base. We're going to change our log instead of, actually, let's do log 10. Log base 10 of x. The same f of x is here. I wrote the 10 out there so that we can remember that that is actually a 10. And so if you remember the change of base formula, the change of base formula is going to give us log of the new base of the x divided by log of the new base of 10. Well, what new base do we want? I don't know. Let's pick natural log. Let's change it to natural log. Why? Because. That's why. So, change of base formula says this will equal natural log of x divided by natural log of 10. We can split this up to be 1 over natural log of 10 times natural log of x. The natural log of 10 is just a number. That's all it is. It's a number. So 1 divided by natural log of 10 is a number. So we have a number times natural log of x. When we have a number times our log, that's a vertical, it's a vertical stretch. And so a change of base is just a vertical stretch, which, if we remember back to the 2 to the 3x, where we did a horizontal stretch or compression, that changed the base of our exponential function. A vertical stretch or compression will change the base of our logarithmic functions. And what's fun is that we could actually take this 1 over natural log of 10, we could move it up to the exponent, and so natural log of x to the 1 over natural log 10 is actually just log base 10 of x. That's something that you will probably never see unless it's like one of those challenge questions like, hey, see what you can do here. But we're looking at, this is a vertical stretch. So that was transformations, and there's so much fun stuff that it does, and it's all related, and it's fantastic. So anyway, don't forget to comment. You know who you are, and be ready for some problems when you get to class. And I will see you then.